Okay, so for this week we're going to be talking about function composition and inverses, two related concepts, and it's primarily going to concern the work that we do in section 8.3, where we define the inverse trigonometric functions. So to begin with, let's talk about what a composition of two functions are. We've talked about how a function is a set of ordered pairs, and we think of the x-coordinate of that ordered pair as being an input, and then the output is some other number that we correspond to the y-coordinate of that ordered pair. What function composition does is it takes the output of one function and then uses it as the input of a second function. So this would be the function g of f of x. That's how we write that. Okay, so as an example, let's suppose that we have this. If f of 1 is equal to 5 and g of 5 is equal to 9, what is g of f of 1? The way we do function composition in this form is we think of working from the inside out. Well, f of 1 is on the inside of these outer parentheses right here, and f1 we're told is equal to 5. So g of f of 1 is equal to g of 5. Notice I've evaluated the f of 1. It's equal to 5 based on the information that I'm told up here. G of 5 we're told is equal to 9. And so what happened was the output 5 was used as the input for the second function g, giving us a new output of 9. Okay, we can do this by defining rules for these functions as well. Let f of x equal 2x, and g of x is equal to, let's say, x plus 1 over x minus 2. Evaluate f of g of, let's say, 3. Okay, well in this case, same idea. I want to work from the inside out, and so that means what I'm going to do is look at what's on the inside. G of 3 is equal to whatever I would get from plugging 3 into this function. So this is equal to, I'm still going to write the f on the outside, f of, and then plug a 3 in for my numerator and denominator. 3 plus 1 over 3 minus 2. That would equal 4 over 1, or 4. Okay? But notice that would be the output of g from plugging in the number 3 as my input. The output is 4. That output then gets passed along to the function f and becomes the input for f. F doubles its inputs, 2x, or in this case 2 times 4, which equals 8. Okay, let's do a little experiment here. What if I evaluated g of f of 3? Notice what I'm doing is I'm still using 3 as my input, but I'm plugging it into f first, followed by g, instead of plugging it into g first, followed by f. In this case, we're looking at g of 2 times 3, because that's how we define the function f, which is equal to g of 6. Again, notice I'm working from the inside out. Then I go to my function g and I plug a 6 into that. That's equal to 6 plus 1 over 6 minus 2, or 7/4. Notice 7/4 and 8, those are not the same number. And so it looks like the order that we evaluate these composition of functions in makes a difference. If you switch the order of f and g, you're not necessarily going to get the same output as a result. Okay? All right. Let me scroll down my notes here. All right, so the next thing I want to do is think about what would happen if I don't plug in a specific number, but if I leave things in terms of x. So this time, let's let f of x equal x minus 4, and g of x is going to equal 3x squared. Evaluate let's say g of f of x. Well, what is that? Notice there's an x here instead of a number like 3. So what this means is I'm leaving everything in terms of x. If I do the same thing that I was talking about before, working from the inside out, g of f of x, that would equal g of, what is f of x? X minus 4. Okay? Now, it may look a little odd to see an expression like this being used as an input, but this is totally valid notation. If I take that x minus 4 and substitute it in for the x that's appearing here in my g of x function, I get 3 times, remember, this input is what we plug in for x. So now instead of x, it looks like x minus 4 squared. I have a couple of options. I could expand this out in the form of a polynomial and distribute the 3 in, but it's actually fine to leave it in this form and just say that that's our answer. Okay, so that's a little bit on function composition. You'll be working with that concept in the assignment for this week. But now let's move on to the concept of one-to-one functions. So we need the idea of one-to-one functions in order to talk about inverses. So what is a one-to-one function? A one-to-one function is a function such that every output corresponds to one, let me write that differently, one and only one input. Okay, now let's think about this for a second. First and foremost, one-to-one functions are functions. So let me do an example to help illustrate this. Determine whether the given functions are, we can write one-to-one this way, or not. Okay, so we're going to look at functions in different forms. Remember, we've said that functions can be ordered pairs. So for the first example, let's consider the following set of ordered pairs. 0, 0. 1, 1, 2, 0, 3, 5. Notice first of all that this is a function because every input, 0, 1, 2, 3, is only associated with a single output. I don't have 0, 0 and 0, 1, for example. We're not getting the same x values going to different y values. However, this function is not one-to-one because in a one-to-one function, we want the reverse of that to be true also. We want every output to only be associated with one input. And if you notice, these two ordered pairs both have an output of 0, but they come from different inputs, 0 and 2. It's still a function, but it's not a one-to-one function. So I say not one-to-one. Okay, here's a set of ordered pairs that would be one-to-one. Pi 0, pi over 2 root 2, negative 1, 1, 5, 6, and let's say 10, 10, something like this. Just a kind of a random function. It is a function. None of the inputs are showing up twice, so there's no inputs going to multiple outputs. And there's also no repeated outputs. I have 0, root 2, 1, 6, 10. None of those outputs show up a second time being associated with two different inputs. So this one is one-to-one. Okay? What about if we're given a function in the form of a graph? Let's suppose I'm looking at a parabola. This is a function because if you remember in our discussion of functions, we talked about the vertical line test. If every vertical line that passes through this curve only intersects the curve once, then we have a function. So that's pretty clearly the case. Any vertical line I put through this this parabola will only ever hit the parabola once. But it's not a one-to-one function, because if I pick a particular output, say this one, let's call that y, that output shows up as the y coordinate of two different points on this curve here. So if I call that x1 and x2, then this would be the point x2y, and this would be the point x1y. Different inputs corresponding to the same output y. That means that this is not one-to-one. But notice the line that joins those two distinct points is a horizontal line. So for one-to-one functions, we have a different test that we call the horizontal line test. This horizontal line also hits the graph in two places. Because of the horizontal line test, we would say that it's not one-to-one. Okay? Let's look at a graph that is one-to-one, one that passes the horizontal line test. Say a graph like this. It's a function because any vertical line will only ever intersect that curve once, and the same can be said of any horizontal line, no matter how I draw that horizontal line. So this one is one-to-one. Okay? A little bit trickier. This should feel very similar to how we dealt with functions previously, but very, very similar to that case is when we're looking at functions that are defined by some kind of formula or algebraic expression or something like that. So let's see, where did we leave off? We were at D. Here's another example. What if I have the function y equals, let's say, 3/5 x minus 1? Okay, is this a one-to-one function or is it not? Well, in this case, it's actually a little bit easier to start by graphing that function and then using the horizontal line test. It can be a lot more difficult to determine whether a function is one-to-one or not by just looking at the way the function is defined. But if I were to graph this function, I know from algebra that this is the equation for a line. It has a y-intercept of -1, and its slope is 3/5. So I would go 1, 2, 3, up to 2, to the right by 5, and I would have a point here. And the graph very roughly looks like that. Obviously, I could have been much more careful for the sake of making a detailed and accurate graph, but the point is not to be accurate. The point is just to determine whether this thing passes the horizontal line test. And I can see that any horizontal line that I put through this curve will only ever intersect it once. It's pretty easy to see that. So this one is one-to-one. Okay? Fairly straightforward. Now, why do we care about one-to-one functions? One-to-one functions are the types of functions that have inverses. And what is an inverse? So an inverse of a one-to-one function, f, is a function that we denote this way. You'll notice I'm using exponent notation here. It looks like f to the -1 power, but it doesn't actually mean the same thing as the -1 power. The literal interpretation of this is just f inverse. That's how we say it. And it's simply another function that's related to f in a particular way that we're about to define. So an inverse of a one-to-one function f is a function f inverse, that's how we read that, such that the inputs and outputs of f and f inverse trade places. Now, this is not a formal mathematical definition, but that's okay because I just want to give you a general idea of what we're talking about. So here's an example. Find the inverse of the function in part B of the previous example. Notice part B we determined was a one-to-one function. And in our definition of an inverse, you can only have inverses of functions that are one-to-one. And when we look at our definition, it says a one-to-one function f has an inverse f inverse such that the inputs and outputs are traded. We trade their places. So basically, I'm going to take each of these ordered pairs and flip-flop them. So instead of pi 0, I'm going to have 0 pi. And instead of pi over 2 root 2, I'm going to have root 2 pi over 2, 1 negative 1, 6, 5. And then if you notice, the last ordered pair 10, 10 has the same input as output, so it's not going to look any different when they trade places. Okay? Now, this is where we can see why the function has to be one-to-one in order for this to work. Take a look at the first part of this example. This function we determined was not one-to-one. What would happen if I tried to trade the places of all my inputs and outputs anyways? Well, this would still look like 0, 0, but this ordered pair would look like 0, 2. So now that I've done that, I have 0 showing up as two different inputs after flip-flopping everything, and that would correspond to two different outputs, meaning the result is not a function anymore. So in order for inverses to be functions, the original function has to be one-to-one in order for that to work. Okay, so just a little bit more to do. Suppose f of 12 equals negative 5. And f is 1-to-1. Find f inverse of negative 5. Well, again, the input in this case up here is 12, and that corresponds to an output of negative 5. Negative 5 being the output here is now being used as the input in my inverse function. So the flip-flop of the inputs and outputs means that the input here is going to become the output here. F inverse of negative 5 is equal to 12. Okay? Fairly straightforward once you have the idea. Okay? I want to do one more example where we look at, let me see. Or sorry, not an example, but I want to show what the role of an inverse function actually is. If we compose a function with its inverse, if such a thing exists, then we should get back to the original input. Here's what I mean by that. Let's take this previous example up here that we did. What if I were to find f of f inverse of negative 5? What would that be? Okay, so remember, we start from the inside. F inverse of negative 5, we worked that out. That was equal to 12. This becomes f of 12. And then f of 12, what's that? Well, in the description of the problem, I'm told that f of 12 is negative 5. And here's something that I want to point out. We ended up with the exact same result as our original input. And the same thing would happen if I did this in the other order. What is f inverse of f of 12, for example? Well, we know that f of 12, based on what we're given, is equal to negative 5. And we also know that the inverse, or f inverse of negative 5 is equal to 12. Again, the result was the same thing that we used as our input. This will be true in general for any composition of a function with its inverse. Okay? In general, f inverse of f of x will equal x. The original input is going to show up as my output if I do a composition of f with its inverse. And the same is true if I do the composition in the other order. F of f inverse of, let's call it y, just to give it a different name, would equal y. Okay? So as a final example, let's see if we can determine if two functions are inverses of each other. are f of x equals 3x minus 1, and g of x equals x plus 1 over 3 inverses of each other. To verify that, the goal is to compose these two functions, f of g of x, but also g of f of x, and show that in both cases, the end result is just whatever my input was, x. So I'm going to do one direction and leave the other direction as an exercise. What does f of g of x look like? Well, based on how we did function composition, I would take my expression for g of x and put it into f. F of x plus 1 over 3. What does that look like, though? If I take this expression and plug it in for the x here, that's equal to 3 times, not x anymore, but x plus 1 over 3 minus 1. Okay? Here I see the 3's canceling out, leaving me with x plus 1 on top, minus 1 right here. And now I have a plus 1 and a minus 1 that cancel out. And if you notice, the end result after all that simplification is just x, the same thing that's appearing as my input in that composition. That's what you want to see happen if these two functions are to be inverses of each other. But the next step would have to be showing that g of f of x is equal to x. And it takes a couple of steps to do that. And I'm going to let you fill in the gaps because it's good practice. Okay, that should give you everything you need to know in order to do this week's assignment.